Hello dear students. So welcome back to my video lectures on the fourth chapter of 11th standard, that is chemical bonding and molecular structure. So students, hope you know what you are doing in the previous video. Yes, we were solving the multiple choice questions to the level of NEET, to the level of JEE mains, and to the needs and deeds of Karnataka CET. So far how many questions we have solved? Yes, I think we have solved the first question. Yes, the second question is done, the third question is done, fourth is finished, fifth, sixth, 7th, 8th, 9th, 10th, 11th, 12th, 13th, 14th, 15th, 16th, 17th, 18th, 19th, 20th, 21, 22, 23, 24, 25, 26, 27, 28, and I think we have solved till 29 questions in the previous video. Now we shall continue with the 30th question. Shall we start with the 30th question? Yes. What is the 30th question? Which of the following has the maximum bond length? Which of the following has maximum bond length? So you have given with O2. Yes, O2 plus, and then O2 minus, and then O2 2 minus. Please correct it because I couldn't type it properly. Yes, you know our chemistry is hard to print because it is full of chemical structures. So which, and moreover I am not good in typing and all. So which one of the following has the maximum bond length? And we have O2. So we have given with O2, O2 plus, O2 minus, and O2 2 minus. We have to just find out which has the maximum bond length. So bond length, remember, if you want to know, if you want to just conclude on bond length, if you want to comment on bond length, then you should be knowing about bond order. You should calculate the bond order of these species. You should calculate the bond order of these species because we know bond order is inversely proportional to bond length. Bond order is inversely proportional to what? Bond length. Bond length. Bond order is inversely proportional to bond length. So which one of the following has the maximum bond length? So if you want to comment on bond length, you should calculate the bond order. Bond order is inversely proportional to bond length. So maximum bond length, when do you say that the bond length is maximum? When you have minimum bond order. Minimum bond order, maximum bond length. Minimum bond order, maximum bond length. Maximum bond length. Understood? Minimum bond order, maximum bond length. Yes. So let us calculate the bond order of these species. How do we calculate the bond order of these species? So for that we have to use the electronic configuration. Configuration that is given as by molecular orbital theory. That is given as we have studied in molecular orbital theory. And what is the formula for bond order? Bond order is equal to half of NB minus NA. Half of NB minus NA. Bond order is equal to half of NB minus NA. So let us calculate the bond order. So if you want to calculate the bond order, you have to write the electronic configuration, not the normal electronic configuration, not the electronic configuration as given by molecular orbital theory. Students, so according to molecular orbital theory, we have two electronic configurations. We have got two different electronic configuration. See, for those molecules or ions with electronic configuration, for those molecules or ion with electronic electrons less than 14 and for those molecules, okay, or ions for which contains electrons greater than 14. Okay, molecules or ions having more than 14 electrons, molecules or ions having less than 14 electrons. So we have a different electronic configuration for this, and we have a different electronic configuration for this case as it is given by molecular orbital theory. So what is the electronic configuration for those molecules or ions which has less than 14 electrons? The electronic configuration is given by, please remember, it is sigma 1s, sigma star 1s, sigma 2s, yeah, sigma star 2s, okay, and then what? Okay, yes, pi 2px, okay, pi 2py, pi 2px, pi 2py, okay, and then okay, what else? Sigma 2pz, yes, and next pi star 2px, pi star 2py, pi star 2py, and then sigma star 2pz, sigma star 2pz. So this is the electronic configuration that we have to follow for the molecules with less than 14 electrons. Whereas for molecules or ions with more than 14 electrons, then there is a slight change in this electronic configuration. What is that electronic configuration? Look here, it is sigma 1s, sigma star 1s, yes, sigma 2s, sigma star 2s, okay, sigma 2pz, okay, pi 2px, pi 2py, okay, and then pi star 2px, pi star 2py, and finally sigma star 2pz, sigma star 2pz. So this is the electronic configuration that we will use for those molecules or ions with greater than 14 electrons. Now coming back to this question. So students, here we have O2, O2 plus, O2 minus, O2 2 minus. Okay, O2 plus. Okay, how about oxygen? One oxygen has 8 electrons, isn't it? And therefore 2 oxygen, 2 oxygen, 2 oxygen, 2 oxygen. So 8 plus 8, 16 electrons. So one oxygen has 8 electrons, therefore 2 oxygen will have 16 electrons. 16 electrons. That means the number of electrons in each of the given species is more than 14. Therefore, which electronic configuration you have to follow? Yeah, we have to follow the second electronic configuration, that is sigma 1s, sigma star 1s, sigma 2s, sigma star 2s, sigma 2pz, okay, pi 2px, pi 2py, pi star 2px, pi star 2py, and sigma star 2pz. Okay, so we have to use this electronic configuration because the number of electrons in each species is more than 14. Okay, now let us calculate the bond order of O2. Let us calculate the bond order of O2. What is the bond order of O2? O2, how many electrons? Yes, okay, yes, how many electrons? 8 plus 8 is equal to 16 electrons, isn't it? 8 plus 8, 16 electrons. So let us fill those 16 electrons in these various orbitals. So we have to follow Hofbauer's principle, Pauli's exclusion principle, and also Hund's rule of maximum multiplicity. Okay, yes, hope you know the rules. So we have to fill those 16 electrons in these various orbitals. How do we fill it? Okay, so 2, yes, 4, okay, 6, 8, 10, okay, 10, 2, 4, 6, 8, 10, okay, yes, 11, 12, 13, 14, 15, 16, okay, isn't it? Yeah, 15, 16, yes, we got it. 2, 4, 6, 8, 10, 12, 14, 16, 15, 16. So shall we calculate the bond order of O2? Look here, bond order of O2 is equal to half of number of bonding electrons. See, sigma star, pi star, pi star. Okay, star represent anti-bonding orbitals. Okay, without star represent bonding orbitals. Bonding orbitals will have bonding electrons. Anti-bonding orbitals will have anti-bonding electrons. Okay, so NB, that is number of bonding electrons. How many number of bonding electrons? Just check. Yes, 2, 4, 6, 8, 10. 10 bonding electrons minus number of anti-bonding electrons 2, 4, okay, 5, 6. So 10 minus 6. So 10 minus 6 is 4. 4 by 2 is 2. Okay. Therefore, the bond order of O2 is how much? Yeah. So let me write it there. Okay. Yes. Okay. Just a minute. Okay. Okay. What is the bond order of O2? The bond order of O2, I don't have a duster here. The bond order of O2 is 2. Okay. Yes. We got the bond order, don't get confused. Yes, okay, we have calculated, and the bond order comes out to be equal to 2. Comes out to be equal to how much? 2. Okay, next let us go with the next one, O2 plus. Okay, what is the bond order in O2 plus? Okay, before that, please count the number of electrons. There are 2 oxygen. Okay, so 8 plus 8 is 16, but it has a positive charge. If it has a positive charge, that means we need to subtract 1 electron. So 16 minus 1 is going to be 15. Okay, so we have to fill the 15 electrons now. Okay, so let us fill the 15 electrons. 2, 4, 6, 8, 10. Okay, 11, 12, 13, 14, 15 electrons. That's it. Okay, 15 electrons. Okay, that's it. There are no electrons here. Okay, look here, 2, 4, 6, 8, 10, okay, 11, 12, 13, 14, 1, 15, isn't it? So okay, yes, what is the bond order? The bond order is, calculate the number of bonding electrons. 2, 4, 6, 8, 10. Okay, number of anti-bonding electrons 2, 4, okay, 5. So 10 minus 5 is 5. So 5 by 2 is 2.5. The bond order of this species is 2.5. Is that correct? Okay, so what is the bond order here? The bond order of O2 plus is 2.5. That's exactly correct. Now next, O2 minus. Okay, yes, let us count the number of electrons in O2 minus. Okay, yes, what is, okay, O2, 8 plus 8, 16. There is minus 1 charge. So if there is minus 1 charge, you have to add 1 electron. So 16 plus 1 is how much? 17 electrons here. 16 plus 1 is 17 electrons. So we have to fill these 17 electrons in these orbitals. Okay, we have to fill these 17 electrons in these orbitals. So shall we fill? Come on. Okay, so let us fill 2, 4, 6, 8, 10, 11, 12, 13, 14, 15, okay, 16 and 117. Is that correct? Okay, just count 2, 4, 6, 8, 10, 11, 12, 13, 14, 15, 16 and 17. Okay, so shall we calculate the bond order now? Yes, the bond order is half of number of bonding electrons. Count the number of bonding electrons. 2, 4, 6, 8, 10. Number of bonding electrons is 10 minus number of anti-bonding electrons 2, 4, okay, yes, 6, 1, 7. So 10 minus 7. Okay, are you getting my point? Just look, 2, 4, okay, 6, 1, 7. Okay, so 10 minus 7 is 3. Okay, 3 by 2. 3 by 2 is 1.5. 1.5. Okay, so what is a bond order? Bond order here it is, okay, 1.5. The bond order of this species is 1.5. 1.5. Are we clear? Yes. Any doubts? Yes. Now the last one, okay, O2 2 minus. O2 2 minus. Yeah, come on. Okay, half of. So how many electrons, by the way? Okay, oxygen, there are 2 oxygen. 8 plus 8 is 16, and there are 2 negative charge, that means you have to add 2 electrons. So 16 plus 2 is 18. So we have to fill those 18 electrons in these electronic configuration. Come on, let us fill it. 2, 4, 6, 8, 10, 12, 14. Okay, yes, 14, 15, 16, 17 and 18 and 18. Okay, yes. So 2, 4, 6, 8. Okay, so 18 electrons. 2, 4, 6, 8, 10. Okay, 11, 12, 13, 14, 15, 16, 17, 18. So now calculate the bond order. Bond order is equal to half of number of bonding electrons. Just count the number of bonding electrons. 2, 4, 6, 8, 10. So number of bonding electrons is 10 minus number of anti-bonding electrons 2, 4, okay, yes, 6, 8. Is that correct? So 10 minus 8. 10 minus 8 is 2. Okay, 2 by 2 is 1. So what is the bond order of O2 2 minus? It is 1. Okay. Now the question is not about calculating the bond order. The question is asking you to find out which of them has maximum bond length. I told you bond length is inversely proportional to bond order. Okay, lower the bond order, maximum will be the bond length. Minimum the bond order, maximum is going to be the bond length. So which of them has minimum bond order? Yes, O2 2 minus has minimum bond order. Okay, O2 2 minus has minimum bond order, hence it has maximum bond length. Lesser the bond order, okay, more will be the bond length. So O2 2 minus has minimum bond order, hence it has maximum bond length. So which of them has maximum bond length? Yes, of course it is option D, O2 2 minus. Okay, students, let us retain these bond orders of O2, O2 2 plus, O2 2 minus, O2 minus and O2 2 minus. Okay, see, this is called as oxygen, normal oxygen. This is called as oxonium ion. Okay, this is what is this? O2 minus, this is called as superoxide. O2 2 minus is peroxide. Yeah, this is peroxide. Okay, yes, this is superoxide. This is oxonium ion, and this is normal oxygen. Let us retain the bond order because, okay, we can expect many other types of questions on the same concept. We can expect many other questions, okay, of the same type. Understood? Okay, so let us retain the bond order of these, okay, oxygen, oxonium ion, oxide and O2 2 minus, and let us finish off all other problems related to this kind. Okay, yes, shall we? Yes. Okay, or else, okay, we will just go ahead, we will take up the next question and we will solve there itself, no issues. Okay, yes. Yes, we will take it up later, no issues. Okay, yeah, students, next question. Let us talk about the next question. Okay, how many bonds does B2 have? How many bonds does B2 have? So if you want to have the number of bonds, then we should again calculate the bond order. Okay, if you want to know the number of bonds, again we have to calculate the bond order. B2, yes, B2. Okay, yes, come on. Boron, Okay, atomic number is 5. Okay, 5 plus 5 is, so boron has, B2 has total 10 electrons. Okay, again you have to calculate the bond order. See, if bond order comes out to be 1, okay, so 1 bond. Okay, if bond order comes out to be 2, then there are 2 bonds. Okay, yes, if the bond order comes out to be 3, then we say that there are 3 bonds. Okay, 3 bonds. What if the bond order, okay, what if the bond order comes out to be 0.5? Okay, 0.5, yeah, we call it as partial single bond. Partial single bond. Okay, we call it as what? Partial single bond. Okay, that's great. Okay, what if the bond order is 1.5? If the bond order is 1.5, then we call it as partial double bond. Okay, yes, mono, less than 1. Okay, more than 0 means partial single bond. Okay, more than 1, less than 2. More than 1, less than 2, that means it is partial double bond character. Partial double bond character, yes. Okay, and if the bond order is equal to 2.5, if the bond order is equal to 2.5, that means more than 2, less than 3, okay, means it is partial triple bond character. Partial triple bond. Partial triple bond character. Partial triple bond character. Is that simple? Okay, any doubts with this? So we should calculate how many bonds does B2 have. How many bonds are there in B2? Okay, so B2 altogether it has 10 electrons. Atomic number of boron is 5. 5 plus 5 is 10 electrons. So again, if you have to calculate the bond order, we should use the electronic configuration given by molecular orbital theory. So which electronic configuration you going to use if the number of electrons is equal to 10? That means less than 14 electrons. So which electronic configuration are you going to use? Yes, we will be using this electronic configuration, sigma 1s, okay, sigma star 1s, sigma 2s, yeah, sigma star 2s, okay, and then come on, okay, pi 2px will have the same energy as that of pi 2py, pi 2py, and then sigma 2pz, okay, yes, pi star 2px is equal to pi star 2py, okay, and then sigma star 2pz. So this electronic configuration you will use when the number of electrons is less than 14. So altogether how many electrons are there? 10 electrons. So we have to fill those 10 electrons in this configuration. So shall we fill the 10 electrons? Yeah, 2, okay, 2, 4, 6, 8, 9, 10. Is it correct? 2, 4, 6, 8, 9 and 10. Follow Hund's rule strictly. Okay, yes. So now calculate the bond order. Bond order is equal to half of NB, that is number of bonding electrons, minus number of anti-bonding electrons. So it is half of number of bonding electrons is how much? 2. Okay, just count. Number of bonding electrons 2, 4, okay, 5, 6 minus number of anti-bonding electrons, okay, so number of anti-bonding electrons, yeah, 2, 4, okay, so number of anti-bonding electrons is 4. So 6 minus 4 is, yeah, 2. So 2 by 2 is 1. So bond order, we are getting the bond order to be equal to 1. Okay, so we are getting the bond order to be equal to 1. So if the bond order is 1, so how many bonds does B2 have? Okay, so B2 has 1 bond. B2 has how many bonds? 1 bond, because the bond order is 1. So if the bond order is 1, okay, we'll say there is 1 bond. 1 bond. Okay, any doubts with this? That's great. Okay, yes. Yeah. Next question, students. Next question. Okay. Yes, students. Next question. Okay. Yes, a metallic bond is, okay, what do you mean by a metallic bond? Okay, the bond that exists in metals is called as metallic bond. What is it? Is it an ionic bond or a covalent bond, a coordinate bond, or electrostatic in nature? What is a metallic bond? We know in copper atoms, okay, copper atoms, okay, there is metallic bond. In any metals there will be metallic bond. Okay, so what do you mean by a metallic bond? See, in case of metallic bond, we know if I take a metal atom, okay, a positive charge, okay, and a negative, electrons will be revolving around the nucleus, isn't it? Electrons will be revolving around the nucleus. Okay, so again if I take one more atom of a metal, okay, again electrons will be revolving around the nucleus. Now what is going to happen here is the electrons of one metal atom will attract the positive charge of another metal atom, okay, and the electron of the next metal atom will attract the positive charge of one metal another metal atom. So this force of attraction is called as metallic bond. And don't you think here the force of attraction is between, okay, opposite charges, negative charge, positive charge, negative charge and positive charge. So if the force of attraction exists between the opposite charge, we say it is purely electrostatic in nature. It is purely what? Electrostatic in nature. So a metallic bond is purely electrostatic in nature, electrostatic in nature. So hence it is option D, option D. Okay, so that's great. Okay, next question. Next question, students. Yes. Okay, the next question says the pair of compounds having identical shapes for their molecules is. The pair of, see, look at here, it has been asked in CET 2014. Okay, Karnataka CET 2014. So those students who are preparing for CET examination, so you have to stress on these type of questions a lot. Okay, so the question is the pair of compounds, okay, having identical shapes, okay, pair of compounds, that means, okay, identical shapes means identical shapes means what? Okay, yes, same shape. And now when do you say that the molecules will have same shape? Okay, if they have, okay, identical hybridization. If they have what? Identical hybridization. Okay, yes, hybridization. So if the, okay, if the hybridization is same for the two molecules, then they have identical shape. Okay, if they have identical shape, then those species are also called as isostructural. Isostructural. Okay, structural. Are you able to understand? Okay, what do you mean by isostructural species? Okay, or isostructural molecules, anything is fine. Okay, what are isostructural species? Okay, species having identical shape. When do you say that the species has identical shape? When they have same hybridization. Same hybridization. Okay, yes. Shall we talk about the pair of compounds having identical shapes for these molecules? Okay, so that means for individual molecules, let us calculate the hybridization. Let us predict the hybridization. So if the hybridization is same, then they'll have identical shape. If they have identical shape, they're said to be isostructural. Okay, they're said to be what? Isostructural. Shall we? Okay, so I'm going to consider the first option. Okay, I hope you know how to calculate hybridization. What is the formula to calculate hybridization? Yes, can I? Yeah, okay, so I'll write it here. I'll write it. Hope you can see this. Yes, identical shape means identical shape means what? Same hybridization. Same hybridization, same shape. Okay, yes, and also when they have identical shape or same hybridization, we say them as isostructural. Isostructural. Okay, so for these individual molecules, we have to calculate the shape, we have to calculate the hybridization, and we have to check for which two molecules or for which pair of compounds the hybridization is same. If the hybridization is same, they have same shape. If they have same shape, they are called as what? Isostructural. By the way, what is the formula used to calculate hybridization? Okay, what is the formula used to calculate hybridization? Well, hybridization is given by the formula half of V plus M minus C plus A. Okay, half of V plus M minus C plus A. Okay, by the way, what is V? Number of valence electrons around the central atom, isn't it? Okay, V means number of valence electrons around the central atom. What is M? M means the number of monovalent atoms around the central atom. Okay, C is total positive charge, A is total negative charge. Okay, total negative charge. Okay, so if the value comes out to be 2, then we say it is sp hybridization, isn't it? If the value comes out to be 3, then we say it as sp2 hybridization. If the value comes out to be 4, we say it is sp3 hybridization. If the value comes out to be 5, it is sp3d hybridization. sp3d hybridization. If it is 6, then sp3d2 hybridization, and if it is 7, we say it as sp3 d3 hybridization. sp3 d3 hybridization. Okay, yeah, now let us check. See, okay, first of all, okay, I hope you know about regular geometry and irregular geometry. Yes, irregular geometry. What do you mean by regular geometry? Okay, yes, if the central atom is surrounded only by bond pairs, if the central atom is surrounded only by bond pairs, then it is called as regular geometry. If the central atom is surrounded both by bond pairs as well as lone pairs, then it is called as irregular geometry. See, for a species to be identical, okay, so for a species, to have identical shapes, they should have, either both of them should have regular geometry or both of them should have irregular geometry. Please note that point. Both the pair of molecules should have same geometry. That means both of them should have either regular geometry or irregular geometry, and they should have same hybridization. Same geometry, same hybridization, then only we can say identical shape. Okay, say if one has regular geometry and the other has irregular geometry, but hybridization is same, no, they will not have same shape. So both of them should be regular or they should be irregular. Only then if they have same hybridization, they'll have same shape. If one has regular and the other has irregular and they have same hybridization, then also they will not have identical shape. They will not have what? Identical shape. So note this point, students. Understood? Okay, that's great. So now look at here. By the way, boron chloride, BCl2, okay, it is actually, there is a printing error, it is BCl2, beryllium chloride. Okay, boron chloride cannot be BCl2, boron chloride has to be BCl3. So there is a printing error here, it is BCl3 and ClF3. Okay, so look here, beryllium chloride, if I consider beryllium chloride and ClF3, students, here which is the central atom among these two? Okay, so here beryllium is the central atom, okay, and chlorine is the central atom. Okay, see, no, just remember one thing, okay, less electronegative atom will be considered as central atom. Will be considered as what? Central atom, except, there are exceptions here, except what? Carbon, nitrogen, oxygen. Okay, we don't consider these, okay, because yeah, I'll tell you where I should consider carbon, nitrogen and oxygen as the central atom. Okay, so usually, okay, less electronegative atom should be considered as what? Central atom. A less electronegative atom should be considered as a central atom. Please note that point. Okay, so here, so we know chlorine is more electronegative than beryllium, hence beryllium is the central atom. Okay, fluorine is more electronegative than chlorine, so chlorine is the central atom. Well, students, beryllium belongs to second group. Okay, so beryllium belongs to what? Second group. Well, second group elements have 2 valence electrons. Okay, correct? Second group elements have 2 valence electrons, no doubt in it. Okay, well, that means beryllium has 2 valence electrons. Well, beryllium has used all the 2 valence electrons to form bonds with 2 chlorine atoms. Okay, so that means beryllium is surrounded only by bond pairs, it is not surrounded by lone pairs. Hence, can I say that beryllium chloride has regular geometry? Yes, beryllium chloride has what? Regular geometry. Excellent. Now, if I consider ClF3, chlorine trifluoride. Okay, well, chlorine belongs to halogen family. Halogen family means 17th group. Okay, well, 17th group elements will have 7 valence electrons. Okay, 17th group elements have 7 valence electrons. Okay, yes. So chlorine has 7 valence electrons. Okay, but it has used only 3 valence electrons to form bond with fluorine atoms. Correct? Okay, the remaining 4 are what? Lone pair of electrons. That means chlorine has both bond pair as well as lone pair. Hence, it is irregular geometry. It is what? Irregular geometry. Okay, so one is regular geometry and the other one is irregular geometry. Even if they have same hybridization, will they have same shape? No, they cannot have same shape. The geometry has to be same. Okay, by the way, let us calculate the hybridization. Okay, yes, see this. For this, let us calculate the hybridization. Half of beryllium, I said there are 2 valence electrons. Okay, plus V plus M, monovalent atoms. Yes, chlorine atoms are monovalent, so there are 2 chlorine atoms. Okay, total positive charge 0, total negative charge is 0, so 2 plus 2 is 4, 4 by 2 is 2. Okay, yes, so 2 means what type of hybridization? Sp hybridization. sp hybridization. Understood? Okay, now let us calculate the hybridization of this atom. Okay, half of V. So number of valence electrons around the central metal atom is 7. Okay, yes, number of monovalent atoms is 3. Total positive charge 0, total negative charge is 0. 7 plus 3 is 10, half of 10 is 5. Hybridization is 5. Okay, 5 means what it is? Yeah, sp3d hybridization. Yes, fortunately students, okay, their geometry is also different, their hybridization is also different. So different hybridization means different shape. Can they be do they have identical shape? No, they do not have identical shape. They do not have identical shape. Okay, so option A cannot be the answer. Okay, so students, I am going slow so that you are able to understand and you will understand all the concepts. Okay, yes, please bear me and have patience. Now let us take the next question. SO2 and CO2. SO2 and CO2. Yes, SO2 and CO2. Okay, SO2 and CO2. Okay, yeah, students, look here. CO2. CO2. Okay, well, okay, yes, SO2, sulfur belongs to which family, which group? 16th group. 16th group. 16th group means 6 valence electrons. 6 valence electrons. Okay, so out of 6 valence electrons, so sulfur has used, okay, 4 valence electrons to form bond with 2 oxygen atoms, because there will be double bond between sulfur and oxygen. Okay, so sulfur has 6 valence electron because it belongs to 16th group. Okay, so okay, it has used, out of 6 valence electrons, it has used 4 valence electrons to form bond with the 2 oxygen atoms. And what about the remaining 2? Remaining 2 are lone pair of electrons. The remaining 2 are lone pair of electrons. So that means it has both bond pair as well as lone pair. So what is the geometry? It is irregular geometry. Irregular geometry. Yes, it has irregular geometry. Excellent. Okay, well, how about carbon dioxide? Okay, so carbon belongs to which group? Carbon belongs to 14th group. Carbon belongs to 14th group. 14th group means 4 valence electrons. 14th group means 4 valence electrons, isn't it? 4 valence electrons. By the way, students, so out of 4 valence electrons, carbon has used all the 4 valence electrons to form bond with the 2 oxygen atoms, because oxygen is divalent. Oxygen is divalent. So carbon has used all the 4, okay, valence electrons to form bond with 2 oxygen atoms. So there are no lone pair, there are only bond pair. So carbon is surrounded only by bond pair. So what type of geometry is it? It's a regular geometry. So here itself you can decide, students. Okay, here itself you can decide that they do not have identical shape, because one is regular geometry and the other one is irregular geometry. Okay, therefore they do not have shape. But anyhow, let us calculate the hybridization. Hybridization is equal to half of V plus M. So valence electrons here is 6. Number of monovalent atoms 0. Okay, total positive charge 0, total negative charge is 0. Half of 6 is, we are getting hybridization as 3. Hybridization is 3 means sp2 hybridization. Okay, okay, now let us calculate the hybridization here. Okay, so half of hybridization is equal to, okay, yes, hybridization is equal to half of number of valence electrons 4. Now monovalent atoms 0, total positive charge 0, total negative charge is also 0. Half of 4 is what? 2. 2 means what type of hybridization? sp hybridization. Hence proved, students. Okay, different hybridization means different shape. Okay, so they do not have identical shape. Okay, understood? Yes. So now therefore see, even option B cannot be the answer. Now let us take up option C. Okay, yes, let us take option C. Okay, in option C we have methane and SF4, sulfur tetrafluoride, methane and SF4. So for methane, students, okay, look at carbon. Carbon, we know it belongs to 14th group. 14th group means 4 valence electrons. 4 valence electrons. So carbon has used all the 4 valence electrons to form bond with the 4 hydrogen atoms. So there are no lone pair of electrons, there is only bond pair. Hence, what type of geometry is it? It is regular geometry. It is regular geometry, isn't it? Yeah. Now, if you take up sulfur tetrafluoride, sulfur again it belongs to which group? 16th group. 16th group. Okay, yes. So 16th group means how many valence electrons? 6 valence electrons. 6 valence electron. So 16 group, 6 valence electrons. So out of 6 valence electrons, it has used 4 valence electrons to form bond with 4 fluorine atoms. Therefore, there are 2 electrons which has lone pair. So sulfur has both bond pairs as well as lone pairs. So what type of geometry is it? Irregular geometry. So one is regular geometry and the other one is irregular geometry, students. Irregular geometry. Hence, what? Okay, they don't have shape. Let us prove it with what? The state of hybridization. Okay, hybridization. Come on, calculate half of. So number of valence electrons 4, number of monovalent atoms 4, positive charge 0, negative charge 0. So 4 plus 4 8 is 8. Half of 8 is 4. So hybridization is 4 means sp3 hybridization. Okay, yes. Next, here let us calculate. Hybridization is equal to half of, okay, your valence electrons is 4, number of monovalent atoms 4, okay, positive charge 0, negative charge 0, 6 plus 4 10, half of 10 is 5. H is equal to 5 means it is sp3d hybridization. Well, this has sp3 hybridization, this has sp3d hybridization. Okay, they have different hybridization. Different hybridization means different shape. Hence, even option C cannot be the answer. So they don't have identical shape, they don't have identical shape, they don't have identical shape. Okay, they have, one has regular, the other one has irregular, and they have different types of hybridization. Therefore, they do not have identical shape. Hence, we have only one option as which is left out. Yes, it is option D. But still, let us check out whether they both have regular geometry or irregular geometry, and they both have the same type of hybridization. Okay, yes. Okay, students. Okay, well, if I consider XeF2 and ZnCl2, let us right away calculate the state of hybridization. Okay, here xenon belongs to which group? 18th group. Okay, 18th group. 18th group means 8 valence electrons. 18th group means 8 valence electrons. Zinc belongs to 12th group. 12th group. 12th group means 2 valence electrons. 2 valence electrons, isn't it? Yeah. Okay, so shall we directly calculate the hybridization? H is equal to half of. Okay, so number of valence electrons is 8, number of monovalent atoms is 2. Okay, yes, number of monovalent atoms is 2. Okay, yes. Okay, so number of monovalent atoms is 2. So xenon belongs to 18th group. Number of valence electrons is 8. 8 plus 2 is 10. Half of 10 is 5. So Z is equal to 5. So we are getting it as sp3d hybridization. sp3d hybridization. Okay. Next. Okay, here if you calculate the hybridization, it is equal to half of. Okay, so number of valence electrons in zinc atomic number is 30. Its electronic configuration is 1s2, 2s2, 2p6, yeah, 3s2, 3p6, 4s2, okay, and then 3d10, 3d10, okay. So total valence electron is, number of valence electron is 2, okay, plus, okay, number of monovalent atoms is 2, total positive charge 0, total negative charge is 0, 2 plus 2 is 4, half of 4 is 2. So we are getting the hybridization to be equal to sp. Here we are getting the hybridization to be equal to sp, but in this case the hybridization is xef2, okay, xef2, okay. Let me check out, students, let me check out. We are getting different hybridization, but in all the other cases also we got different hybridization, but in this case we got different hybridization. Let me check out, okay. Yes, I'll check this question and I'll give you the answer later, okay. Yes, okay. Yes, next question, students. Yes, next question, okay. Yeah, the correct arrangement of species in the decreasing order of the bond length between carbon and oxygen in them. It is also, okay, it has been asked in Karnataka CT 2014, okay. You have to, okay, correct arrangement of the species in the decreasing order of bond length between carbon and oxygen in them is. So you have to arrange them in the decreasing order of bond length between carbon and oxygen, decreasing. The correct arrangement of the species in the decreasing order of bond length between carbon and oxygen, decreasing order of bond length between carbon and oxygen. Okay, so we have been given with, look here, CO2, yes, CO2, 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 and HCO2 minus, HCO2 minus, HCO2 minus, HCO2 minus, CO, 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 CO3 2 minus, CO3 2 minus, and then, yeah, CO, CO, CO3 2 minus. So in all the options he is given 4 same compounds, okay. So he has given CO2, again I am not good in typing, CO2 has been given, then H, okay, CO2 minus is given, okay, HCO2 minus is given, and then what else is given, CO is given, and then CO3 2 minus is given, okay. Yes, so all the species are given. So you have to arrange them in the decreasing order of bond order, sorry, in the decreasing order of bond length, in the decreasing order of bond length, okay. Yes, yeah, carbon dioxide, HCO2 minus, okay, yes, and then what is it, HCO2 minus, or it is, I don't know, HCO2 minus, okay, yes, CO and CO3 2 minus, okay. So students, we have carbon dioxide, what is the structure of carbon and carbon dioxide? It's linear, and there is double bond between carbon and oxygen. Students, there is double bond between carbon and oxygen, CO2, double bond. So double bond means, okay, bond order is equal to what? 2. Bond order is 2, okay. Yes, double bond between carbon and oxygen, double bond between carbon and oxygen, so the bond order is 2. Now if I consider HCO2 minus means HC double bond O, O minus, HC double bond O, O minus. But look here, here we have one double bond between carbon and oxygen and one single bond between carbon and oxygen, okay. That means, do you say the bond order is 2 for this and the bond order is 1 for this? Here there is double bond between carbon and oxygen, here there is single bond between carbon and oxygen. So do you say that the bond order of this 2 and the bond order of this is 1? No, actually this is resonance stabilized, students. See, this negative charge will move here and the pi electrons will be shifted to this oxygen, So that if this is one resonating structure, the other resonating structures is going to be COO minus double bond O. Now look at here. So this the bond order of this carbon and oxygen is going to be 2 now, and the bond order of this carbon and oxygen is going to be 1. Earlier it was 2 and 1, now it is 1 and 2. What do you say? This is the second resonating structure. Okay, what will be the resonance hybrid of the two species here? Yeah, the resonance hybrid is going to be like this. We will write the resonance hybrid: partial double bond, isn't it? Partial double bond. Okay, so the negative charge, okay, is delocalized between the two oxygen atoms. So now what is the bond order? Okay, they do not have complete double bond, single bond, double bond. That means this bond is partial double bond, this bond is partial double bond. So since it is partial double bond, so what is the bond order? Bond order is 1.5. Yes, bond order is 1.5. Okay, clear? Yes. So here for this species the bond order is 2, and for this species the bond order is 1.5. So for the next species, carbon monoxide. Yeah, what is the structure of carbon monoxide? Here we have a complete triple bond between carbon and oxygen. We have complete triple bond between carbon and oxygen, complete triple bond. So what is the bond order? Triple bond means bond order is 3. Okay, complete triple bond between carbon and oxygen. So therefore the bond order is how much? Yeah, the bond order is 3. And lastly, CO3 2 minus. Look at here students, C double bond O minus O minus. So this is what? CO3 2 minus. So understood? Okay, so do you say that this bond order is 2 and this bond order is 1 and this bond order is 1? Bond order is 1, bond order is 2, bond order is 1. Is that so? No. Here also this is also resonance stabilized. Okay, how is it resonance stabilized? Look here, this negative charge will be displaced here. Okay, and this pi electrons will be shifted to the next oxygen. Okay, hence this is the first resonating structure. And what is the second resonating structure? So this oxygen will get negative charge now, and here there will be double bond, and this bond remains as such. This bond remains as such. So this is one resonating structure, and this is the second resonating structure. Okay, second resonating structure. Understood? The other possibility is then this negative charge may be shifted here and this pi electron will be shifted here. Therefore one more possibility is C double bond O. Okay, C double bond O. This oxygen gets double bond now, this oxygen gets negative charge, and this oxygen gets negative charge. So this is the third resonating structure. Okay, now look here, okay, so one time this carbon and oxygen has double bond, the other time single bond. Next, one time this carbon and oxygen has single bond, then double bond. Okay, next one time this carbon and oxygen has single bond, double bond, single bond. That means, so between all the three between the carbon and the three oxygen atoms, there is partial double bond. Isn't it? Partial double bond. Okay, and the negative charge is oscillating between the three oxygen atoms. So what is the bond order? Okay, see, more the number of course the bond order will, since it is partial double bond, the bond order has to be 1.5. The bond order has to be 1.5, but since this also bond order is 1.5, here also the bond order is 1.5, but this has only 2 resonating structures. Here there are 3 resonating structures. So more the resonating structures, lesser will be the bond length. More the resonating structures, lesser will be the bond length. That means this bond order is less than 1.5. Okay, even though there are partial double bond between carbon and oxygen, since there are more number of resonating structures, more than resonating structures, lesser will be the bond order. Okay, is that simple? Yes, less than 1.5. So I have told you students, okay, well, bond order is inversely proportional to bond length. Okay, yes. As the bond length increases, as the bond order increases, bond length decreases, isn't it? So what you are supposed to do? Okay, we are supposed to arrange the species in the decreasing order. decreasing order. So which has highest bond order? Okay, decreasing order of bond length. Decreasing order of bond length. Okay, yes, bond, if bond order is more, bond length is less, because bond order is inversely proportional to what? Bond length. Okay, so well students, this carbon monoxide has bond order equal to 3, so it has more, bond order is 3, bond order is 2, bond order is 1.5, and bond order is less than 1.5. So more the bond order, lesser will be the bond length. Okay, so I can say that carbon monoxide has least bond length. Okay, yeah, carbon monoxide has least bond length. Okay, so its bond order is 3. More the bond order is, lesser will be the bond length. So after 3 we have carbon dioxide. Okay, its bond order is 2. Okay, bond order is 2. Next, okay, we have 1.5. It is HCO, okay, 2 minus. Here the bond order is 1.5. And lastly we have what? CO3, 2 minus. Here the bond order is less than 1.5. Okay, and now more the bond order, lesser will be the bond length. So what is the order of decreasing bond length? Yes, CO3, 2 minus has more bond length than HCO2 minus, then carbon dioxide, then carbon monoxide. Hence what is the correct answer? CO3, 2 minus, then HCO2 minus, then CO2, then CO. So what is the correct answer? The correct answer is option D. Okay, so students, I'll continue with this in the next video also. Thank you.